Every chip ever made has metal sprayed into it. Layer after layer of copper and tungsten wiring, deposited atom by atom onto silicon wafers in vacuum chambers the size of a refrigerator. The machines that do that spraying and the ultra-pure metal discs they consume were supposed to come from a handful of Western and Japanese companies. One of those companies, Applied Materials, has been the dominant force in this equipment category for decades. And yet, right now, a Chinese toolmaker sits reported around 5th in the global rankings for semiconductor deposition equipment, inside the top 5 of a market Applied Materials helped define. Before you file this under China catching up in something niche, the wiring is not niche. Every chip, at every node, from the power controller in your car to the unit training the latest artificial intelligence model, runs on interconnects built by deposition tools. This is not one product line. It is the process every fab on Earth runs thousands of times per wafer. If China controls the tool that lays the wiring and the metal the tool consumes, it controls an input that is invisible to most analysts, but structurally unavoidable in every chip ever built. By the end of this, you will understand how the wiring layer works, why it was the overlooked entry point, how far up the stack China's supply chain has actually climbed, and where the real ceiling still sits. Because this is not a story about one toolmaker outcompeting Applied Materials. It is a story about a supply chain building a floor, layer by layer, from raw metal to refinery to tool, until the question is no longer whether China can access deposition technology, but how much of the stack it already owns. 3 questions will stay open as you follow this story. The reported 5th place ranking keeps coming up. But what does reported actually rest on? And does it hold at leading-edge nodes or only at mature ones? The purity standard for the metal going into these tools is so extreme that a stray atom means a dead transistor. So where exactly does China's refining capability fall short of that standard? And why is that gap so hard to close? And the wiring has been called the nervous system of the chip. But the process recipe for laying it down is where the real accumulated know-how lives. What is a process recipe, and why does it matter more than the tool itself at the frontier? Those 3 threads all resolve. Follow them. To understand how China got here, you need to understand what the machine actually does, and why this particular machine was the one foreign control did not lock down as completely as the lithography scanners. A modern chip is not a flat thing. It is a tower. The transistors live at the bottom, etched into silicon, but they are useless in isolation. To connect them into a working circuit, you need wiring. Metal traces running horizontally across each level of the chip, and metal columns punching vertically between levels. In a leading-edge chip today, that stack can have 10 to 15 metal layers, each deposited separately, each performing a specific job. Copper carries the current between transistors across each floor. Tungsten fills the vertical plugs, the vias, connecting floor to floor. The physics chose those 2 metals deliberately. Copper has the lowest electrical resistance of any practical wiring metal at this scale. Tungsten handles the brutal temperatures near the transistor without migrating out of position. Everything else would perform worse. The industry had no choice. Now picture how those metals get there. Inside a vacuum chamber, smaller than a dishwasher, evacuated to pressures lower than the surface of the moon, a plasma is struck. That plasma bombards a dense disk of metal called a target. Atoms are knocked free from the target's surface and drift across the chamber in a fine metallic mist, settling onto the wafer in a layer measured in nanometers. This is physical vapor deposition. For copper wiring, it runs thousands of times across a wafer's production life. The target is a solid disk of ultra-pure metal, often 12 or 18 inches in diameter, to match the wafer it feeds, and it must be pure, not simply clean. Refined to 99.9999% purity, 6 nines, what the industry calls 6N. One stray atom of iron or sodium per million copper atoms can corrupt a via, and a corrupted via is a dead connection, and a dead connection is a chip that fails. The target looks like a simple thing, a heavy disk of reddish metal. It is not simple at all. Think of the chip's wiring like the electrical system in a skyscraper. Copper conduit running horizontally across each floor with tungsten columns connecting floor to floor. Deposition is the crew that installs both, one floor at a time, in a chamber the size of a carry-on bag, in a vacuum. Now imagine that crew has to work to tolerances where a human hair would be a catastrophic obstruction. That is the process. Applied Materials built its market leadership on, and that is the process China decided to replicate. For decades, the assumption was that Applied Materials and a small set of peers, Japanese and European equipment makers alongside them, had built a moat around this process that would take generations to cross. The assumption rested on something real. Unlike extreme ultraviolet lithography, which depends on a single irreplaceable source of light and a proprietary optical chain that only one company on Earth has mastered, physical vapor deposition does not have one single unobtainable component. The barrier is not one lock with one key. It is systems integration, process repeatability across thousands of production wafers, and recipe libraries accumulated over decades. Hard to crack, but not physically constrained to one supplier's patent on a photon source. That distinction mattered enormously. If extreme ultraviolet is a vault with one key in one city, physical vapor deposition is a high-security combination lock, complex, genuinely difficult, but workable by a well-funded team with enough time and enough failed attempts. When export controls tightened, rules out of the United States Bureau of Industry and Security in 2018 expanded further in 2022 and 2023. China had already identified which doors were combination locks and which were vaults. Deposition was a combination lock. The investment accelerated accordingly. Why did it still take so long? Because process repeatability at nanoscale across thousands of wafers is genuinely hard. The recipe libraries, temperature curves, gas flow ratios, plasma power parameters took incumbents decades to optimize. China's toolmakers had to rederive much of that empirically, running wafer after wafer to identify and correct each failure mode. That work is slow and expensive, even with substantial government and industrial funding behind it. But the path was there, and they took it. The climb happened on 3 tracks simultaneously. Tool hardware came first: vacuum chambers, plasma sources, wafer handling systems that could achieve the cleanliness and precision the process demands. Process recipe development came second, often reverse-engineered and iteratively improved using data from actual production runs. Customer lock-in through price and local after-sales support came third, giving domestic fabs a reason to accept the performance risk of switching to an unproven vendor. What made this different from previous attempts by new entrants is the testing ground. Analysts and industry observers have consistently reported that China's primary logic fab, SMIC, served as the main qualification customer for domestic deposition equipment, a captive testing environment willing to run thousands of qualification wafers on tools that were still maturing. Think of it as a flight simulator for NORA and for AMEC, the company known as Advanced Microfabrication Equipment, a controlled setting where the tools could accumulate real-world production hours without the commercial penalty of failing on a paying external customer. Western incumbents qualified their tools across dozens of fabs with different process requirements on different schedules. China's domestic tools qualified primarily at one fab running mature node processes at volume, which turns out to be exactly the node range where the floor raising matters most commercially right now. The output of that process is the ranking. By most analyst estimates, 3 Chinese semiconductor equipment makers now sit inside the global top 20 by revenue. Nora is reported around 5th, and that hedge matters because the ranking is analyst estimated, not independently audited. It could be 4th, it could be 6th. What is confirmed with more corroboration is that Nora and advanced microfabrication equipment both have deposition product lines running in production at Chinese fabs at mature nodes, meaning 28 nanometers and above. That is not a claim. That is reflected in fab procurement records and output data. But the tool is only half the story. What goes inside the tool, the metal disc the plasma bombards, is where the supply chain becomes genuinely surprising. China produces approximately 40% of global refined copper. By raw metal supply, it is already a dominant node in the global copper chain. But the deposition target is not simply refined copper. It is copper refined to 6N purity, consistently, batch after batch, with metrology precise enough to certify each disc before it enters a vacuum chamber. Refining copper to 6 is like filtering a swimming pool until it contains fewer than 1 grain of sand per 10 Olympic pools of water, and then doing that reliably at industrial volume with a traceable certificate for every batch. That is the gap. Japan's Mitsubishi Materials and JX Metals and Western specialists like Materion in the United States have historically led in ultra-high purity semiconductor-grade target manufacturing. China has a domestic target maker in Griken Advanced Materials, which produces physical vapor deposition targets and whose product lines and customer references are corroborated. But whether Griken's highest purity products meet leading-edge specification at confirmed production volume, that has not been independently verified. The reported gap at sub-7 nanometer spec is exactly where that open thread about the stray atom resolves. The problem is not making ultra-pure copper once in a laboratory. The problem is making it consistently, at volume, with the measurement tools to verify it, for the most demanding wiring layers in the world's most advanced chips. That is an unsolved problem domestically, as best as the public record shows. So the floor has been raised in the tool layer. It has been raised partway in the materials layer, with the purity gap acting as a ceiling on the materials side for the most advanced applications. Now look at where the real ceiling sits on the tool side. A process recipe for advanced copper interconnect is not a software file you can copy. It is a library of thousands of interdependent parameters. Wafer temperatures controlled to fractions of a degree, plasma power profiles tuned to the specific geometry of one manufacturer's chamber, barrier layer sequences, typically tantalum nitride deposited beneath the copper to prevent it from migrating into the silicon, whose exact thicknesses govern how long the wiring survives before it fails through a process called electromigration. In advanced chips, electromigration lifetime is a metric measured across millions of hours of projected use. Tuning it correctly requires understanding failure modes that only reveal themselves after years of production data. Applied Materials and its peers have built these recipe libraries across multiple technology generations, at multiple nodes, in multiple fab environments. The library is the moat, not the machine. China's toolmakers, running primarily at 28 nanometers and above, have derived working recipes for those nodes. That is confirmed by the production output. But the frontier recipes for sub-7 nanometer copper interconnect, the wiring inside leading artificial intelligence training chips and advanced mobile processors, remain largely foreign-originated or foreign-licensed. The domestic recipe status at that level is simply not independently confirmed in any public record. That is not a diplomatic hedge. That is the honest state of the evidence. The tool is a vessel. The recipe is the knowledge of what to put in it and when. At the frontier, that knowledge still largely originates outside China. Does that make the ranking misleading? Only at the frontier. At mature nodes, the nodes that build automotive chips, industrial controllers, power management circuits, analog devices, and the embedded compute infrastructure of most of the world's consumer electronics. The recipes are well established, Chinese tools are confirmed running them, and the floor is genuinely raised. The ceiling matters enormously for artificial intelligence training hardware and leading smartphone processors. The floor matters enormously for almost everything else, and almost everything else is a very large market. By most analyst estimates, from groups including TechInsights, Omdia, and TechInsights, whose numbers on this point have been broadly consistent, mature nodes account for the majority of global wafer starts by unit volume. Not revenue. The leading-edge fabs generate disproportionate revenue on far fewer wafers. But by the number of chips actually manufactured and shipped, the mature node is the dominant layer of the global chip economy. Automotive chips that govern engine management and safety systems, industrial sensors and controllers, power management integrated circuits in every device with a battery, analog and mixed signal chips that interface between the physical world and digital systems. The physics of many of these applications, high voltage tolerance, extreme temperature, analog precision, does not require leading-edge nodes and may never. A power transistor in an electric vehicle does not need a 3-nanometer process. It needs a process optimized for voltage handling, and that process lives at mature nodes. The leading-edge node is the penthouse, expensive, impressive, where the most valuable tenants live. The mature node is the rest of the building. More floors, more tenants, more total square footage, and the structure the whole thing rests on. Here is my honest read on what that means. The triumphalist version of this story says, China has effectively localized its deposition supply chain and is closing in on full independence. That is wrong. The process recipe gap at sub-7 nanometers is real and not closed. The 6N refining gap at leading-edge confirmed volume is real and not closed. Applied Materials leadership at the frontier is intact. The dismissive version says a few rankings and some domestic toolmakers amount to managed decline dressed up as progress. That is also wrong. 3 domestic toolmakers in the global top 20 by analyst estimates, a material supply chain that is partly domestic and growing, and confirmed mature node production readiness at Chinese fabs. That is not theater. The floor is real. It is already in production. It already changes the geometry of any negotiation about supply access. The most important strategic fact in this story is not the ranking itself. It is that China's mature node deposition supply chain has crossed the line from government-stated aspiration to operational alternative with real customers. That is a different kind of leverage than matching the frontier, quieter, more durable, and much harder to sanction away. The floor China has raised in deposition, tool, target, refining, does not threaten the ceiling Applied Materials holds at the frontier. But a floor does not need to reach the ceiling to be structurally consequential. Load-bearing is enough. So here is what I genuinely want your read on. Does it matter more that China has raised the floor on the layer the world's chip volume actually runs on, or that the ceiling of leading-edge process recipe knowledge still sits firmly outside its reach? One side says the floor is already the decisive ground. The other says the ceiling is the only prize worth counting. I want your honest answer in the comments, and I want the reasoning, not just the pick. Subscribe if you want to follow whether China closes the recipe gap at the frontier, or whether the mature node floor turns out to be the more durable strategic advantage. That is exactly what this channel tracks. One copper target, spinning in a vacuum, atom by atom, building the wiring of a chip. The machine holding it is increasingly Chinese. The metal inside it is increasingly domestic. The recipe that tells the machine what to do, that part is still being written.